Hello everyone, this lecture is a review of basic biostatistics from first year and data analysis from second year. In addition, some statistical tests and interpretation of results will form part of the lecture. It is expected that by this time you are more or less halfway through data collection. So let us review the methods for describing data, the appropriate statistical tests for analyzing data, the measures of association in the analysis of two-way tables, and how to interpret the results of a descriptive and inferential statistic and a measure of association. There are basically two methods for analyzing data: descriptive and inferential analysis. Descriptive analysis entails summarizing and presenting data in text, tables, and graphs, while inferential analysis involves making generalizations or conclusions about a population based on the result from a sample, either via estimation or hypothesis testing. And it is with hypothesis testing where statistical tests are utilized. There are basic rules for writing numbers, and this will be dealt with in a separate lecture on technical writing. With regards to interpretation of results in tables, there are two common errors. One, comparison based on absolute numbers, and two, the use of wrong denominators in computing for percentages. Let us take a look at this example. A research question is posed on the proportion of diabetics among those with a family history of diabetes, specifically if the proportion is higher. If one's interpretation is based on absolute numbers, the number of diabetics is lower among those with a family history of diabetes. But the question specifies a proportion, and so it cannot be answered if using absolute numbers. The use of the grand total as the denominator will give 20.7%, which is obtained by dividing 270 by the grand total 1,305. But 20.7% is the proportion of diabetics without a family history among the general population. If the column total is used as the denominator, it will generate 56.3% as the answer, which is obtained by dividing 270 by 480. But 56.3% is the proportion of those without a family history among those with diabetes. And finally, using the row total will give the correct answer, which is 40.4%, derived from dividing 210 by 520. One can correctly conclude that the proportion of diabetics among those with a family history is higher, which is 40.4%, than those without, which is 34.4%. A lot therefore depends on what is asked and what the study objectives are. We now go to graphs. Each type has its purpose. This is a pie graph on the type of healthcare facility among respondents to a survey on attitude and perceptions on COVID-19 pandemic. A pie is used to show breakdown of a group or total when the categories are not too many. Some sources peg it at 5, others at 8. The arrows shows or indicate the ordering of the segments, which starts from the 12 o'clock position running clockwise, from the largest to the smallest proportion, coinciding with the darkest to the lightest shade. The vertical bar graph is used for comparison of absolute or relative counts, that is percentages or rates, between categories of a quantitative discrete variable. The number of depressive symptoms is the quantitative discrete variable and is placed on the x-axis, and the absolute counts, which is the number of respondents presenting with depressive symptoms, is placed on the y-axis. Comparison between categories or groupings are made on the basis of the heights of these bars, and it can be seen that most call center agents have been experiencing at most 2 depressive symptoms for the past 2 weeks. The horizontal bar graph, on the other hand, is used for comparison of absolute or relative counts between categories of a qualitative variable. For this example, the qualitative variable type of disposal containers is placed on the y-axis, and the absolute count, which is the number using a particular disposable container, is placed on the x-axis. Comparisons between categories or groupings are made on the basis of the lengths of these bars. From the graph, majority of healthcare workers dispose used sharps and needles using punctured-proof containers. The component bar graph is preferable over pie in situations where the compositions of two or more groups are to be compared. In this example, there were more of household cleansing agents ingested in self-poisoning and more of hydrocarbon ingestion in accidental poisoning cases. The histogram represents the frequency distribution of a quantitative continuous variable. The horizontal axis is a continuous scale bearing the continuous variable C-reactive protein. The vertical scale shows the absolute counts of patients falling within bounds of particular CRP levels. If the midpoints of these bars are connected and their endpoints joined to the horizontal axis to close the figure, what we have is a frequency polygon. This is advantageous if two or more distributions are to be depicted in a single graph, such as, for example, comparing C-reactive protein levels between mild and severe COVID cases. A line graph is used to show changes of the variable with time. The time variable year from 2011 to 2020 is placed on the x-axis, and the total number of dengue cases is placed on the y-axis. As noted in three regions of the Philippines, NCR, Region 4B, and Region 8. The peak that is noted in 2019 coincided with the reported dengue outbreak in most regions in the country. By 2020, there was a noted decline in the number of cases concurrent with the COVID-19 pandemic. To show the relationship between two quantitative variables, preferably quantitative continuous variables, a scatter plot is best. A perfect upward straight line indicates a direct positive, high, and significant degree of correlation between the variables. The quantitative continuous variable is pulse rate, taken using manual method and via pulse oximeter. This is a summary of the type of graph, the nature of the variable, and its use. The third type of describing and presenting data is through the use of summarizing figures, which can be qualitative or quantitative. Under qualitative, we have measures of frequency and location, and under quantitative, we have measures of central tendency and dispersion. Measures of frequency refer to counts, which can either be absolute or relative. Relative counts are your ratios, proportions, and rates. Counts and proportions are used to describe and summarize nominal and qualitative ordinal data. Measures of location refer to percentiles, deciles, and quartiles, which are basically used to compare a given value with some normal or standard value, as in measurements of ability and intelligence, determination of normal range of laboratory values, and interpretation of growth charts. Under quantitative measures, you have measures of central tendency and measures of dispersion. As a review, measures of central tendency are the mean, median, and mode. The mean, which is the average, is used to describe and summarize ratio data. The median, which is the middlemost observation, is used to describe and summarize quantitative ordinal, interval data, and skewed numerical data. The mode, which is the most frequently occurring value in a set of observations, is used to describe interval and ratio data. The degree of spread or variability in the data is provided by the measures of dispersion, since the average alone is not enough to describe a set of observations. The range is simply the difference between the highest and the lowest value. The wider the range, the more dispersed the data. The variance, conceptually, is the average of the squared deviations from the mean. The mean is the reference point, such that any deviation or difference from the reference point gives an idea of how close or how far the individual values are from the mean. The implication is the greater the variance, the more dispersed the data, the farther the values of the individual observations are from the mean, and the more imprecise the estimate. And standard deviation is just the square root of the variance. Another measure of dispersion is the interquartile range, which is the difference between the 25th and the 75th percentile, or the first and the third quartile, and basically contains the central 50% of the observations. The wider the difference, the more dispersed the data. The choice of what summary measure to use, whether mean, median, or proportion, will depend on the scale of measurement and the nature of the distribution. As a review, there are two basic types of variables: quantitative, where they are expressed numerically, and qualitative, where they are grouped into categories, and you have the following examples. And there are four scales or levels of measurement. Under qualitative, you have nominal and ordinal. And under quantitative, you have interval and ratio. Ordinal can also be quantitative. In nominally scaled variables, the classes to which individuals or objects may be assigned are numbered or named, and they are best summarized and described using counts or proportions. In ordinally scaled variables, the classes to which individuals or objects may be assigned are ordered or ranked. There are two subtypes: qualitative ordinal, which are best summarized and described using counts or proportions, and quantitative ordinals such as ratings and scales. Example, your visual analog scales for pain assessments and Likert scaled responses. These are best described and summarized using the median. In interval scale, there are exact or equal distances between categories of the variable, and the 0 point is arbitrary. They are best described and summarized using the mean, the median, or mode, but not ratios between data. The 0 point is fixed in ratio-scaled variables such that meaningful interpretations can be made between numbers. They are best described and summarized using the mean, median, and mode. With regards to the nature of the distribution, if it is symmetrical or normal or the curve is bell-shaped, the following summary measures, mean, median, and mode, can be used interchangeably because they are all found in the center of the distribution. But if the distribution is skewed, the median or mode is preferred because it is not affected by extreme values. If skewed, the mode will still be the highest point on the curve. The median is the middle between the mean and the mode, and the mean on the outermost portion of the curve because its value is affected by extreme values. How do I check for skewness? You can output a histogram or check the value of skewness from an output of the descriptives of the data. This slide shows how descriptive statistics can be generated in Excel using the Data Analysis Toolpack and clicking the options Descriptive Statistics and Summary Statistics. This will give you the results: the mean with the corresponding standard deviation, median, mode, range, minimum and maximum values. Using SPSS, go to Analyze, scroll down to Descriptive Statistics, then click Descriptives. Under Descriptives, click the summary measure you are interested in. And you have the results. This is the computer output of the descriptives using the Explore option. For qualitative data, to generate descriptive statistics using SPSS, go to Analyze, Descriptive Statistics, then Frequencies, then indicate the variable to be counted. The second type of analysis, which is inferential analysis, entails estimation and hypothesis testing. In estimation, you are trying to deduce that the findings obtained from a sample can be generalizable to the population. With hypothesis testing, you are trying to determine if the results from a sample is significantly different from some standard or reference value or from a comparison group. These are examples of estimating a population mean, which is the motivation score of work-from-home office workers in the National Capital Region during the 2020 COVID-19 health crisis, and estimating a population proportion, which is the proportion of work-from-home office workers in the NCR with low motivation. The single number represents the point estimate, and the two numbers represent their lower and upper limit of the interval or the interval estimate. While the process of hypothesis testing involves the use of a statistical test, you start by stating the null and alternative hypothesis of the study. Data is collected and analyzed. The significance of the result is determined by running a statistical test. When the probability of occurrence under the null hypothesis is true, the sample results support the null hypothesis, and therefore it is not rejected. But when the probability of occurrence is low, meaning the sample results do not support the null hypothesis, the decision is to reject it in favor of the alternative hypothesis. There are several factors to consider in the choice of the statistical test, and all of these have to be taken into consideration simultaneously. As a review, the first factor to consider is the objective of the study, and it can fall into the following major types. 1. Comparison with some pre-specified value, be it a mean or a proportion. Second, comparison between two or more groups on a mean or a proportion. And third, relationship or correlation or association. The other considerations are type of variable, whether qualitative or quantitative, scale of measurement, whether nominal, ordinal, interval, or ratio, the number of samples, whether two or more than two, and the relatedness of the sample, whether they're paired or independent, and the assumption on the distribution, parametric for bigger sample sizes and numerical data, and non-parametric for smaller sample sizes and non-numerical data. This table classifies the test to use based on the objective of determining differences between groups, the level of measurement, mean for ratio, median for ordinal or skewed numerical data, number of samples, whether two or more than two, and the relatedness of the sample, whether independent or related, and the assumption on the distribution, whether parametric or non-parametric. This table classifies the test to use based on the objective of determining differences between groups, the level of measurement, proportion for nominal or qualitative ordinal data, the number of samples, two or more than two, the relatedness of the sample, and the assumption on the distribution. Here's another way to look at it, through the use of an algorithm to help one decide what appropriate statistical test to use based on the factors to be considered. This table classifies the tests to use based on the objective of determining relationship between study variables according to the level of measurement. The succeeding slides will show the most frequently used statistical tests with computer outputs of results and the corresponding interpretation. So given this example, the objective is on difference between two groups on a variable oxygen saturation, which is ratio. And so the objective is on the difference between groups on a mean. There are two groups accounting for the two modes of delivery, normal spontaneous delivery versus cesarean section. and they are independent or unrelated. The null hypothesis is that there is no difference in the oxygen saturation between those delivered by NSD versus those delivered by cesarean section. And the alternative hypothesis is that there is a difference. So given these factors, what is the appropriate statistical test? The appropriate statistical test to determine difference in oxygen saturation between NSD and cesarean section is the independent t-test. The independent t-test answers the research question on whether the mean of two independent groups are equal, but the following assumptions have to be satisfied before an independent t-test can be carried out, the most important of which is normality of the data. The issue is of less concern if the sample size is at least 30 in each group, since the distribution is more or less normal at sample sizes equal to 30. There are ways to check violations of this assumption. One is looking at the descriptives of the data, if the mean is equal to the median in both groups and if skewness is equal to 0. Next is to output a histogram to see if you have a normal, symmetric, and bell-shaped curve. And lastly, run a test for normality, which is the Shapiro-Wilks test. An insignificant p-value on such test implies that data can be assumed to be normal. This slide shows how the analysis can be generated using Excel. The independent t-test generates a highly significant p-value, which is less than 0.0001. Another way to do it, if there is no data analysis toolpack, is to use the formulas option, scroll all the way down to statistical, and then to t-test. This slide shows the analysis using SPSS. The data is formatted as such. Delivery is coded as 1 for NSD and 2 for cesarean section, and is contained under the column variable delivery. The arrows are used to move O2 saturation under the test variable and delivery under the grouping variable. The grouping variable delivery is defined based on the codes 1 for NSD and 2 for cesarean section. These are the results as seen from the computer output. The basis for making a statistical decision whether to reject or not reject the null hypothesis are a significant p-value, which is less than 0.05, a high test statistic value, and a 95 confidence interval of the point estimate, which is the mean difference, which does not include the null value of 0. To remind everyone, computer outputs have no place in your final manuscript. The results should be presented in a manner that can be easily understood. For this particular case, you have a table showing your mean and standard deviation of the oxygen saturation of the two groups and a column for the p-value corresponding to the test that was used. The next example involves three groups compared on systolic blood pressure, which is ratio scaled, and calls for hypothesis testing. So given these factors, what is the appropriate statistical test? Using an algorithm based on factors to be considered in the choice of the statistical test, the appropriate statistical test to determine differences in systolic blood pressure between the three drugs is one-way ANOVA. The ANOVA is used to test hypotheses about more than two population means by analyzing the variances of the observed data. This variation is attributable to differences within groups and between groups. The simplest type is your one-way ANOVA, in which only one source of variation or factor is investigated. The data in SPSS and how to run it The test statistic is known as the F-test, derived from dividing the mean square between groups to mean square within groups. The p-value for the test is significant. It is less than 0.05, which means there were significant differences in systolic blood pressure between drug types. But it does not specify in which drugs the differences lie. This is addressed by doing your post hoc analysis or multiple comparisons test. By clicking on post hoc, it specifies the choices for your post hoc tests. The results show that the differences in systolic blood pressure were between drugs 1 and 3 and drugs 2 and 3. For this next example, the objective is on comparison or difference between groups on the variable handedness, defined as the proportion who were left or right-handed, which is nominal in scale. And so the objective is difference between groups on a proportion. There are two groups, male and female, and they are independent or unrelated. The null hypothesis is that there is no significant difference in handedness between males and females, and the alternative is that there is a significant difference. Given these factors, what is the appropriate statistical test? The appropriate statistical test to determine difference in handedness between males and females is your chi-square test. The chi-square test is used to find out whether two or more populations have the same proportions for the different categories of another variable. This slide shows how the analysis can be generated using SPSS. This is the computer output of the analysis showing the value of the test statistic, which is 0.034, which is quite small, and the p-value, which is not significant, 0.854, and it's greater than 0.05. Therefore, with an insignificant p-value, the null hypothesis is not rejected, and the conclusion is there is no significant difference in handedness between males and females. The chi-square test is applicable to data only if the expected frequencies are sufficiently large, and the criteria for being sufficiently large depends on the size of the table as defined in this slide. In our example, all expected frequencies are more than or equal to 5. That is why chi-square test was applied. If the assumptions are not satisfied, Fisher's exact test is used, such as in this particular example. Under tests to investigate relationship between variables, the choice of the test depends on the scale of measurement. The chi-square test of association is used for examining the existence of a relationship between two qualitative variables, which is gender and smoking status in this example. We use the same chi-square test regardless of how we state the research question, whether as a difference in proportion between groups or association or dependency between variables. The logic behind the chi-square is that if no relationship exists between gender and smoking status, meaning that gender and smoking status are independent, the observed frequencies, which are in black, will be the same or close to the expected frequencies, which are in red. And the value of the chi-square statistic will be small. If a relationship or dependency occurs, the observed will vary from the expected, and the value of the chi-square will be large. This is how the chi-square test statistic is computed manually. Excel generates the result on the cross-tabulated observed values and computed expected frequencies. To analyze, go to Formulas. Under More Functions, click Statistical, then chi-test. Place the observed frequencies under the actual range. Then the expected frequencies under the expected range, then click OK. Excel returns a p-value which is less than 0.05 and therefore highly significant. In SPSS, from Analyze, go to Descriptive Statistics, then crosstabs. Transfer gender as the row variable and smoking status as the column variable. Click on chi-square as the test statistic. The output shows the test statistic value and the p-value for the test. With correlation, the main objective is to determine and quantify the extent to which one quantitative variable x varies with another quantitative variable y, without necessarily assuming that y is dependent on x. The caveats in correlation are that it does not prove causation and it is non-directional or bidirectional. The first property implies that R, or rho, or the correlation coefficient, can either be a positive or negative number. With reference to direction, positive values imply a direct relationship, meaning high values of y are correlated with high values of x, and vice versa. Negative values imply an inverse relationship, which means that high values of y are correlated with low values of x. And lastly, magnitude. That is, the nearer the value is to 1, the stronger is the correlation. As seen in this slide. For this example, the objective is on correlation between variables, body mass index and hand grip strength, which are both quantitative continuous, specifically ratio scaled. And in our table, Pearson product moment correlation is appropriate. The null hypothesis is that there is no significant correlation between BMI and hand grip strength, and the alternative is that there is a correlation between the two variables. This slide shows how the analysis can be generated using SPSS. Results show there is a positive, high, and significant correlation between BMI and left hand grip strength, and a positive, moderate, and significant correlation between BMI and right hand grip strength among females. Positive, meaning the higher the BMI, the stronger is the hand grip strength, and vice versa. This is a scatter plot of the correlation between BMI and left hand grip strength. We now go to measures of association in the analysis of contingency tables. The risk ratio or relative risk is the measure of association for cohort study designs. It is the ratio of the incidence of disease among exposed relative to the ratio of disease among those not exposed. In this example, the investigator wishes to determine if a low allergen maternal diet can reduce crying and fussing in the infant, which are symptoms of colic. The exposure variable is the control diet containing allergenic food proteins, and the outcome is non-significant reduction in the crying and fussing of the infant. This slide shows the analysis using open source EpiInfo. The results show a risk ratio of 2.5, that is the risk for non-significant reduction in the crying and fussing of the infant is 2.5 times more among those exposed to control diet versus those on low allergen maternal diet. The interpretation follows the definition of the risk ratio, that is the risk of disease or condition among exposed versus unexposed. The odds ratio is the measure for association in case control study designs. It is the ratio of two odds, the odds of exposure among cases versus the odds of exposure among controls. In this example, cases were those with esophageal squamous cell carcinoma, while controls were those without esophageal carcinoma. The exposure was drinking hot to very hot tea. Using open source EpiInfo to generate the results, we get an odds ratio of 3.05. This means those with esophageal squamous cell carcinoma were 3 times more likely to have consumed hot to very hot tea than those without esophageal squamous cell carcinoma. For those doing regression analysis, the following slides only show the basic concepts in regression. In correlation analysis, the main objective is to determine and quantify the extent to which one quantitative variable X varies with another quantitative variable Y, without necessarily assuming that Y is dependent on X. The relationship between X and Y is described by means of a single number called the correlation coefficient. In regression analysis, the relationship is described by means of an equation of the curve which best fits the data. It involves determining an equation for predicting the value of the outcome from the values of the explanatory variables. The outcome in linear regression is a continuous variable. If there is a single dependent and independent variable, it is known as simple linear regression. When two or more independent variables are considered simultaneously, the technique is called multiple linear regression. The outcome or dependent variable in logistic regression is categorical and may be binary, as sick or not sick, or polytymous, as in mild, moderate, severe depression. The independent variables may be continuous and categorical. This is an example of using linear regression technique on data on the amount spent on medical bills per month and the number of household members of 10 randomly selected households in Laguna. Is there a relationship between household size and medical expenditure? What is the expected medical expenditure for a household size of 8? The computer output provides the equation or the formula for the relationship between monthly medical expenditure and household size, and interpreted as follows: that for every member increase in household size, there is a corresponding 258 peso increase in the household's monthly medical expenditure, and household size significantly predicts a household's monthly medical expenditure. And likewise predicts the monthly expenditure for a household size of 8 using the derived equation from the data. Logistic regression estimates the risk or probability of disease or outcome as a function of several exposure or independent variables. The independent variables can be qualitative, such as personality type, smoking, or quantitative, such as age, cholesterol level, and blood pressure. In this example, birth weight is the binary outcome variable, dichotomized as low birth weight and normal birth weight, and the following maternal factors were considered as the independent variable: smoking status, history of hypertension, presence of uterine irritability, and number of physician visits during the first trimester. With modeling, study variables with insignificant p-values were sequentially removed until all that remained were those significantly associated with low birth weight, which were smoking status, history of hypertension, and presence of uterine irritability. The final logistic regression results show that those with low birth weight were 1.94 times more likely to smoke, 4.06 times more likely to have a history of hypertension, and 2.78 times more likely to have uterine irritability than those with normal birth weight. The contents of the data analysis part of the final manuscript should contain the statistical techniques used in relation to the study objectives. In summary, we have two types of statistics, descriptive and inferential. Descriptive involves presenting data as text, tables, or graphs, or computing for summary figures. Inferential statistics involves estimation of a mean or a proportion, and hypothesis testing, which is basically the use of statistical tests for the following objectives. And we have the analysis of 2 by 2 tables, which involves computing for measures of effect or association, such as the risk ratio and the odds ratio. These reminders reflect common errors committed in relation to the data analysis and results section of the final paper. So the description of the data analysis should reflect or should coincide with the study objectives, specify the statistical software package used, and for SPSS, use the version that is in our institution, which is SPSS version 22. In the results section, these are the following reminders. These are my references. Thank you for listening and see you at the forum.